Okay, good afternoon, and thank you for the invitation. What I want to cover today is the specific issues of using ABC methods, ABC standing for approximate Bayesian computation, in doing model choice from a Bayesian perspective, and actually doing model choice through Bayes factors. So I'll just recall very quickly what approximate Bayesian computation is, and then go into the problem linking ABC and Bayesian model choice before completing the picture by trying to give some indications as to when we can use ABC for doing model choice. That is the latest results we obtain in this field. So the starting point for doing ABC is that there are cases where the standard approximation tools based on Monte Carlo methods, namely producing a sample that is roughly from the target distribution, in the Bayesian case, a posterior distribution, is not possible because of the complexity of the likelihood function. So for instance, we may have a latent variable model where there are so many latent variables that the integral of f of yv against dz is impossible either analytically or through simulation, just because of the sheer size of the latent space z. And so in such cases where f of y given theta cannot be computed numerically, we cannot directly use MCMC. So that, I mean, there are many counterexamples where I cannot produce a numerical value for f of y given theta and still run MCMC. But there are also many examples where we can't. And so that's where the ABC method occurs. It's not exactly Bayesian, it's almost Bayesian, but it produces some reasonable approximations to Bayesian inference, or maybe in some cases only. That's what I want to talk about. So, I mean, I will skip the illustrations. The starting point of ABC methods is population genetics, and in particular phylogenetic trees, where when the phylogeny itself was not of interest, but only the parameters driving the tree were of concern for the geneticists, integrating over the trees, all the possible trees, was such an impossible task that they started doing these approximation methods that led to ABC. So what is ABC? Well, the starting point is B for Bayesian. So we have a posterior distribution, pi of theta, f of x given theta. And because we cannot compute f of x given theta, we run simulation instead, and simulation of the data rather than the parameters. So the ABC algorithm starts from this remark that is very simple, that if we simulate parameters from the prior, then pseudo data conditional on those parameters, and wait for the pseudo data to be equal to the observed data, the outcome, so the resulting theta primes that come out of this loop, are from the posterior distribution, because the probability of acceptance is exactly f of y given theta prime. Okay, so that's a very simple remark. It's like accept reject 101. Because the probability of acceptance in that case is 0 or 1. Okay, so that's an exact algorithm for running simulations from the posterior distribution without computing the posterior distribution. Of course, that's useless in most situations, either because the distribution f is over a continuous space, or even in a discrete space because the space is too large for waiting for z equal to y. And so that's where the A comes into the game, that we cannot wait for v equal to y, and therefore we accept a tolerance zone around z equal to y and get out of the loop when z and y are close enough by a tolerance condition that is rho of y and z less than epsilon, epsilon being a positive number and rho being a distance. Okay. So of course this induces an approximation, and the outcome is not from pi of theta given y, but pi of theta given roughly y, that is the zone of rho yv less than epsilon. So that's the starting point of the ABC algorithms, namely that we will accept for loss of information by diluting the information contained into Y for producing simulations. Otherwise, we couldn't get simulations. Okay, so the algorithm is very easy to write and to implement. We keep generating from the prior distribution. We generate pseudodata from the likelihood, which implies that, of course, we must be able to produce pseudodata. And then we wait until the pseudodata is close enough to the true data using yet another approximation, and that will be the central point of the talk, namely that instead of waiting for the data and the pseudodata to be close enough, we go through a summarizing statistic, eta, and so we wait for eta of z and eta of y to be close enough. And in most cases, eta is not a sufficient statistic, and therefore we have another degradation of the information contained in the data because we throw away some part of the information. And the reason for doing that and for using summary statistics that are of smaller dimensions than the data is because usually waiting for the whole data to be close to the pseudodata is, again, impossible when you think about time series, for instance. You cannot wait for a few thousand points to be close to another few thousand points. So there is a curse of dimensionality there that we need to go through a reduction in the dimension, even though this implies a loss of information. It's a kind of paradox that we get more information by reducing the dimension than by keeping the whole data. Okay, so in the long run, if we have a lot of computing power and we can push epsilon to 0, in the best of cases, what we'll get is an approximation to pi of theta given eta of 1. Okay, that's the best possible outcome. And so in some cases, we do get reasonable approximation to the original Bayesian target. So I won't explain the details, but I just use a benchmark data from R, the Pima Indian woman benchmark data set, where we use a probit modeling of the probability to get diabetes, and using a Bayesian modeling to estimate the 3 parameters, beta 1, beta 2, beta 3, out of the 200 observations, we do get an approximation by ABC that is very close to the MCMC approximation to the posterior distribution. So in some cases, we don't get any loss of information. Of course, that's the toy example where we would not need ABC because we have the MCMC outcome. All right. So there is a whole literature and a lot of directions about ABC. But to link with the topic of today, ABC is very primarily used for conducting model choice. And so doing model choice with ABC is straightforward because in a Bayesian approach, model choice is simply an estimation of yet another parameter, namely the index of the model. So if you introduce the label of the model as an extra parameter, and you put this extra parameter into the picture, you just have to run ABC on this larger space that includes the model index. And so we want to derive the posterior probability that the model index is equal to m given the data. Well, the ABC approximation can produce such an evaluation by running simulations from the prior, which means that we have two steps where we simulate from the prior for the model index, and given the model index, we simulate a parameter value from the conditional prior. And so we have a pair m and theta m, and given m and theta m, we generate pseudodata, and once again, we wait for the pseudodata to be close enough to the true data. Okay, so that's the generic ABC model choice that will run and produce a frequency for different model indices, and those model indices will hopefully converge to the posterior probabilities that m is equal to m given some aspect of the data. We are losing information, so it's not exactly pi of m given y. But if t goes to infinity and epsilon is close enough to 0, we should get something that resembles the posterior probability that m is equal to m. Okay, so I mean, those are questions I had at the beginning when we're working with ABC model choice, but I will skip them because Actually, I have more questions than that. So we started looking at this problem in one very specific example, that is a Potts model, where the only parameter is the strength of the interaction between the points on the structure, like a graph or a grid. And we ended up having fairly nice approximations to the true posterior probability that the model was the one we were considering. So I think I'll skip that too. The point that it was working was about sufficiency, because let me skip to the general issue. If you start with two models, M1 and M2, each of them with a sufficient statistic eta 1 and eta 2. So if eta 1 is sufficient for model 1 and eta 2 is sufficient for model 2, the pair eta 1, eta 2 is not necessarily sufficient for the pair M theta M. Of course, eta 1, eta 2 is sufficient for theta 1 in model 1, for theta 2 in model 2, because we take a larger vector. But for identifying the model index, we may lose the efficiency. And in the case of Potts model, this was not occurring. That by merging sufficient statistics together, we were preserving sufficiency across models. So what is occurring with ABC is that it may hit this difficulty by just sheer use of insufficient statistics. So just in a few slides, let me show you the limiting behavior of the base factor based on the ABC outcome. So if we start from the practical approximation to the base factor when comparing model 1 and 2, we are simply taking the ratio of the frequencies of acceptance of model 1 over acceptances of model 2. Okay. Now, if we let t go to infinity, we have the Monte Carlo error that goes away, and we end up with a ratio that is this ratio of the probabilities that the distance between eta of y and the simulating eta in model 1 is less than epsilon over the same probability in model 2. Okay, so this depends directly on the posterior distributions of eta in model 1 and in model 2. Now, if I let epsilon go to 0, and I remove the approximation effect of ABC, I end up with something that is totally predictable, namely that by having an infinite computing power, ABC produces a base factor that is based only on the summary statistics. Okay, so if I have a summary statistic eta, the best I can do is to look at the base factor based solely on eta of y. Okay, so I'm making a decision when using ABC model choice that only depends on eta of y. If I run a base factor and the standard Bayesian model choice procedure. Now the question is, how much do I lose by using this eta of y rather than y? And to show how much I lose, let's consider a priori favorable case where eta is sufficient under both models. This never occurs in practical cases, but that's an ideal case just to look at the difference. If I am in a sufficient situation in either model, I have a factorization of the likelihood into a term that doesn't depend on the parameter and the density of eta. So the likelihood breaks into those two terms, and therefore when I compute the base factor, those terms get out of the integral and appear as a ratio in front of the ABC base factor, or more precisely, the base factor depending on eta only. And therefore, in the most ideal of cases, the base factor that we are aiming at, the thing we would like to compute to decide which model is the most appropriate for the data, is not the base factor we are practically computing, but a ratio times this base factor. And the difficulty is that this ratio doesn't have to be equal or even close to 1. Okay? The only case where it is equal to 1 is when eta is sufficient for the pair m theta m. If it's not sufficient for m, this ratio is of any order from order 1 to order n, the size of the data. So this can get to totally different directions from this one. Okay, so the inference based on b eta may be completely different from the inference based on the original B12. And that's why using the base factor in an ABC setup with sufficient or insufficient statistics may lead to different conclusions as to which model is the most appropriate for the data. Okay. So there is a potential danger for discrepancy there. So let me show you a silly example of a Poisson versus a geometric model. So I have a sample x1, xn of size n that I consider could either be generated from a Poisson or from a geometric distribution. And in both cases, the sufficient statistic is the sum of the observations, so the sum of the xi's from 1 to n. And this sufficient statistic is not sufficient across models in the sense that if I take the ratio g1 over g2, I don't get 1. I get a quantity that varies with the data, and therefore implies that this summary statistic is not informative about which model is relevant for the data, which makes sense when you think about it, because S is a single number, and you don't want to decide about whether it's Poisson or geometric based on S equals 3, for instance, right? So there is not enough information in S, but that's, for our purpose, that's something significant. And if we compute the base factor based only on S, we get nonsense, in the sense that it won't tell us anything about which model is right. Actually, it's always picking the geometric model, whether the data is on the left Poisson or on the right geometric. And there is no connection with the true base factor, which is indicated by the scale at the bottom of this graph. Okay. So it's not surprising, but that tells us that we may lose a lot of information by not considering carefully the choice of those summary statistics. Of course, in this toy example, because we are within an exponential family, things can be recovered by a formal result, namely that if we embed both families into a meta exponential family that contain both of them as special cases, by using the cumulant moment functions, T1 and T2, we do recover a summary statistic that is sufficient across models. And in that case, we can conduct inference without losing information. The base factors based on eta 1, eta 2, T1, and T2 is then the same as the base factor based on the whole data set X. But of course, that's a specific case that only occurs because of the exponential nature of both distributions. In the general case, we would not be able to find this embedding feature. So the question is, what is the meaning of the base factor when using ABC with a summary statistic that is not sufficient across models? Okay. And there is no global answer. In some cases, it may produce answers that are close to the true base factor. And this is an example where we do get the same conclusion, although numerically we get very different answers. So I ran a simulation with data that is from an MA2, moving average of order 2, trying to compare MA1 and MA2. And the four bar plots are using epsilon from 10% to 0.1% of the distances. You can see no variation across those epsilons. And the answer to the experiment is that in two cases out of 3, I would pick MA2. So the base factor would be roughly 2 in that case. The true base factor, when you use the whole data, is 17. So I'm leading to the choice of MA2 as if the data is MA1, I'm picking MA1. but with numerical values that are very different from the true base factor, even when I push epsilon to be very close to 0. Actually, I'll skip that example. And just to introduce the next step, at some point last year, we had reached this level where we are not confident about using ABC for computing base factors with summary statistics. Okay, and so our temporary conclusion at that time was to stick to model assessment evaluations, that is model by model, trying to check whether the model was fitting the data based on the ABC run for this model, rather than being more formally Bayesians and believing into the posterior probability of one model against another. Because I mean, there are cases where you can use the whole data and not throw away information, but there are other cases like these population genetic examples where you cannot definitely use the whole data. And so we started another experiment by trying to find conditions under which ABC model choice base factor would be correct. So to get back to the formal Bayesian answer of using posterior probabilities for models. And so this is the last part of the talk with results we obtained in that direction. They are much more formal than the previous results, in that they are considering consistency, which is the weakest possible evaluation we could give. Namely, we have to wait for the data to grow to infinity with no Monte Carlo error and no tolerance in ABC. So we are just pushing very far from the practical case. But surprisingly enough, the conclusion we get on the summary statistics are of practical value, which you have to wait to the end to believe. So you have to bear with me through a few slides of math. Well, the starting question is very global. It goes further than ABC. Namely, if you take a data set Y and you turn it into a summary statistic that is degrading the information contained in the data. So you have T of Y that is insufficient across models. When is the base factor consistent? That is, when does the base factor select the right model, almost surely as the data size grows to infinity. And there are global results when using the whole data that under regularity conditions, the base factor will be consistent, assuming the parameter space doesn't grow to infinity and things like that. But if you reduce a vector of size n into a vector of size d that is fixed as n grows to infinity, does it still work? Okay. So we are not any longer considering an approximation of B12 of y. We have given up on that level. We are only considering BT12 of y. It's a base factor based on T of y. Okay. And to start with yet another toy example that was suggested through the editorial process of the previous paper, take two models that are location models, either the normal with parameter θ1 or the Laplace with parameter θ2. And the Laplace is parameterized with 1 over root 2 to make both variances equal to 1. That's why it's not 1. And consider four possible statistics that are the sample mean, the sample median, the sample variance, or the median absolute deviation, or MAD. The two first statistics are informative about theta. Y bar is sufficient for M1 but not for M2. The third and the fourth statistics are ancillary. And despite its name, the best statistic will be the MAD one. So here is an illustration of the performances of one of the three first summary statistics. If I keep simulating from model 1 and compute the probability that model 1 is the right one, I get this brown curve. It is a probability that the model is normal, given that the data is normal, tends to accumulate around 0.6, 0.5, 0.6. If I simulate data from a Laplace distribution, I get the blue curve. We see that the probability also accumulates around 0.5, 0.6. So I have no discrimination based on this experiment to say that the possible probability will pick the right model. Okay? Another representation of this variability is this one. That is, the possible probabilities do accumulate in the same region. So there is no information containing these possible probabilities. Now, if I use a MAD statistic, I do get this accumulation, namely that under model 1, things tend to accumulate around 1. Under model 2, things tend to accumulate around 0 and not 2. Which is exactly what I want. It means that if the data is from Gauss, the possibility will get towards 1. But if the data is not from a normal distribution, it will get close to 0. So this statistic, the force statistic, has the right behavior for conducting the model choice. Although it's definitely not sufficient because it doesn't bring any information about the parameter. Okay. And so this different behavior will be hopefully identified by our consistency results. So the structure is therefore to start from a data set that comes from a certain distribution Pn. The summary statistic has a projected distribution Gn, that is of dimension d, that is fixed for n. That's the starting point. And then we compare under both models posterior distributions that are of the form pi1 and pi2 that are only conditional on Tn. And the question is, what is the behavior of the corresponding base factor as n grows to infinity? And to prove any result, we have a sequence of 4 assumptions that are found in standard Bayesian asymptotics that I describe first, and then we can skip about them. The first condition is a regular central limit theorem that tells us that Tn converges to its mean at a speed Vn with a limiting distribution Q. So Q is a normal distribution. Vn is root of n in most cases. Condition 2 is about the large deviations of Tn around mu theta when away from the true mean. So there is something like that where we control what Tn minus mu of theta I does when mu I is not mu naught. Mu naught is the true mean of Tn. Okay. There is a third condition which tells us about the behavior of the prior distribution around the true mean of Tn. And it gets worse at each assumption, but it's almost over. So it tells us that when mu of theta I is close to mu naught, so this is the variability of the mean of Tn under model I, this is the true mean of Tn. Well, the behavior of this ball as Vn grows down to 0 is of order Vn minus di. And the important factor here is di, which tells us that the ball may lose some dimension as n grows to infinity. So Tn is not necessarily informative about all the directions. This is the only important fact. And the fourth assumption is a behavior of the model density against the true density, which tells us that it's essentially bounded by the limiting density in a neighborhood of the true mean. Okay. Right. So we need those assumptions to get to this result, which essentially contains the consistency and the inconsistency result. Namely that if mu naught, the true mean of the summary statistic as n grows to infinity, is contained in the range of the means of Tn under model I, so if the infimum of this difference is 0, then the marginal distribution of Tn under model I has a behavior that is of order Vn d minus di. in particular when di is d, the dimension of Tn, it says that essentially, asymptotically, the marginal of Tn is roughly constant. Okay, there are two constants to bound MR. On the opposite, if mu naught is not within the range of the mu I of theta i's, which means that definitely model I cannot be the right model. So if MI is not the right model and doesn't contain mu naught, then in that case, MI of Tn goes down to 0 at a speed that is either d minus tau I or d minus alpha. So what this says is that if mu naught is not included in this range, the marginal distribution will pick the discrepancy and go to 0. If mu naught is within the range, then the behavior is totally dictated by Vn d minus dr. And therefore, in terms of consistency, within each model, there is consistency in that the marginal picks the wrong model at this bit. Between model, the result is fairly simple, namely that all that matters is the mean of Tn, not its limiting distribution, not over moments, but only its mean value. Namely, if the mean value of Tn is eventually within the range of the mu I of theta i's, there is no way that the model will pick the fact that it is not the right model. I mean, or the procedure will not pick it is the right model. So in the case where mu naught is within both ranges for both models, as was the case for y bar, for instance, in my example, then the ratio of the marginals, which is exactly the base factor, behaves as Vn to the d1 minus d2. So it's only a battle of the respective sizes or dimensions of the models. It has nothing to do with the true model. Okay? So the smallest model will always win in that case. Okay? So it depends only on this difference. There is no consistency. On the opposite, if one of the two models doesn't contain mu naught, so it's identified as the wrong model, and this one is like the pseudo-true model, maybe it's even the true model, then in that case, M1 over M2 grows correctly to pick the right model, that is 1 in that case. And so the consistency is that there is no consistency if the ranges contain, both ranges contain mu naught, and there is consistency in the other case. So let me show you an example. The first remark is that, of course, if we can pick ancillary statistics that have different means under both models and that are not constant, we do get a way to identify the model. Now, this is not always possible. Of course, there are more ancillary statistics than there are sufficient statistics, so we don't need to remain within exponential families. This is the most interesting case, of course, because that's the easiest to establish. But in complex models, it's not necessarily the case that we can come up with ancillary statistics. So maybe I'll have time to show one example where we try to identify the right statistic. In other cases, we have to run simulations where we identify that for the theta i's of interest, the means are different. So another example on Laplace versus Gauss, by using the force moment. So the force moment is not a necessary statistic. Its expectation depends on theta under both models. And the means are different in the sense that mu1 of theta is not the same as mu2 of theta. But unfortunately, there exists theta and theta prime such that mu1 of theta is equal to mu2 of theta prime. And in that case, we get this kind of behavior, or in terms of variability, we get that thing. So even though the force moment is different for, say, the true theta for mu1 and mu2, because the ranges may cover the true value of mu naught, we end up with this lack of efficiency of the base factor in that case. We cannot, using only the force moment, we cannot pick the right model. The same thing is true for the sixth moment. Now, if we mix the sixth and the fourth moment, then there exists no theta that can recover the mean, the same mean under both models, and then we get consistency. And in that case, we use the moments because we can prove that all our assumptions hold, but that's not so important. What's important is that in that case, we do get this exclusion of one model under each of the models. So using the two moments, that is the fourth and the sixth moments, we do get an exclusion. Now, in practice, and this could be my last slide, how can we proceed to recover which statistics are right and not? Well, with the outcome of an ABC on each model, we have estimates of the parameters under each model. And next, we can check whether the mean of the statistics of interest are the same or different under these estimated parameters. So we don't need to rerun ABC for a whole series of parameter values. We have the estimated parameters that are the preferred parameters, the closest to the true parameters. And so we can run this kind of experiment that is very cheap compared with the ABC experiment, namely that for each statistic of interest, so here I took X bar and the median, we can check whether the means of those statistics are different. So this is a T statistic for the mean and the median. And you can see that within the range -2 and 2, all our simulations do produce values inside this range. And so the conclusion is that X bar or the median are not interesting statistics for conducting the comparison. For the variance, the empirical variance, and the MAD statistic, we didn't need to run such an experiment because they are clearly ancillary statistics, so one single run is enough. The explanation of the first axis is that we run ABC based on X bar, the median, the MAD statistic, and the variance, and the interquartile statistic, just to see how things were moving, and we did get this outcome. So in conclusion, model selection can be done via ABC using the base factor. We just have to be very careful about the choice of the summary statistic. In estimation, there is a push for having less summary statistics to be more precise. So the curse of dimensionality is pushing for as little as possible summary statistic, as in the latest paper by Fernand and Prangle, who show that using an approximation of the posterior expectation is somehow the best summary statistic. In testing, it's somehow pushing higher rather than lower, in the sense that we must have a different behavior of the summary statistic so that this holds, namely that we cannot recover the same mean under both models. And in the most complex models, this cannot be done through computational techniques. So I mean, the last word is a word of warning, but for the positive warning rather than negative warning. Thank you. Questions?
So, for the particular summary statistic, might you expect better out-of-sample performance than a model fitted with standard MCMC?
ABC is almost, I mean, necessarily worse than MCMC. If you can use MCMC, you don't have no reason to use ABC.
I was thinking it could be better maybe for the particular choice of statistic. I think it's kind of like fitting a model according to just predictive check. So
No, I mean, no, I see no. I mean, after you can start arguing about computing time and things like that, but on a methodological basis, there is no reason. You throw away some information. I mean, the MCMC again, I mean, if it's very slow, then you start getting into this issue of, well, you have to compare computing time and things like that. But on principle, MCMC is producing an outcome from the true posterior using the whole data. Here, you have necessarily something approximative. Now, if you need something quick and dirty, yes, of course, you can you push the dimension as low as possible. You run an ABC. You have a lot of models. You want a lot of estimators. Yeah, this could be a solution. But you are for a given model. I don't see any argument for not degrading the quality compared with the true outcome.
How does it work in practice, the method you're suggesting? So you have your large set of simulations under both models.
Under both models.
And you look at all the space of summary statistics you can construct based on that have the right properties, that the means are not relative.
Yeah, so this is the example for two statistics. Well, so I mean, you just take the two first columns, right? So you have your ABC estimation for each model, for the normal and here's the Laplace. Using this theta hat, you produce an estimator, a sample from the summary statistic under both models, and you compare the mean of those two samples. So you compute a t-test.
But you don't have a setup to guide your choice of summary statistic. You try anything that comes to mind or you think is appropriate. I mean, you could imagine
we are not
lead to some sort of selection that would maximize the separation between both models.
No, we are not there. What would have been nice would have been to find the similar result as Fernand and Prankel, that for estimation, the best summary statistic is the posterior expectation. Here it would have been the base factor, but actually it's not true. It's not true at all. If you use a base factor, you get you get the wrong answer.
Any other question?
Yeah. Yeah. Zero. Yeah. No, not exactly. Well, clearly, but actually that so the prior was an exponential one. The prior on theta was an exponential one, and so we wouldn't get samples that were too much zero. So I mean, this graph was made on the marginal, not for a given data set, but for a collection of data sets. So, but the result was that the base factor based on the sum was fairly constant around 1/2 or something. Well, I mean the prior ratio was 1, right? You would put the same weight on each model. But yeah, eventually pushing the data to 0, you should get 1. I believe I would get the right answer. Because I mean it's the overall answer is that there is, even for large data set, the base factor varies very close to 1. So if we were to push the prior close to 0, it should come even closer to 1. Yeah. I mean, it's easy to check. I can check later.
Yeah.
You briefly mentioned about some method from
Yeah, so this was my conclusion last year in ABC in London. That's where I stopped. That if you have statistics that do not reduce the data into something less informative, this discrepancy that is the center of the talk totally vanishes. Of course, in practice, you have all the difficulties, like the tolerance is not zero. Having a small tolerance may be hard, and so there is some blurring of the data, but it's not at all the same issue that we may lose completely the right information.
So I was thinking, I haven't really, I've used ABC. I've never actually done a model choice problem before. I've never really confronted any problem, basically. But Mark Fermont, published something a few years ago with getting a regression model, basically just simulating a lot of data sets from the different models under those relatively priors. And then, essentially, I imagine this is a kind of ad hoc thing that doesn't correspond to the exact Bayesian procedure, but you've basically picked a multi-nodal regression model where each of the categories are the different models, and so you use that to kind of predict or assign. And so I didn't look into that properly, but I imagine there's a whole lot of things along those lines that are sort of somewhat ad hoc procedures that might have good performance in different situations, but I don't know. Do you have any views on that?
Yeah, that's exactly this slide. That if you use the Mark's logistic correction, you do get an improvement towards the diagonal, again, say the true posterior probability. That the shrinkage effect of the logistic brings the code is that the blue dots are closer to the diagonal. Even when we throw away some summary statistics. So this is without the ABC logistic correction, and with the correction we get back. So we do recover information because, as you say, we run. It's a bit ad hoc, but we run the best weight on the different summary statistic for selecting the model. So we just given that we are in each model, we do use extra information, and so we're getting away from the true base factor, but essentially we get a better performance. Yeah. So that's a very good comment. In that there are ways, if we don't stick to the exact base factor, that are more tolerant of this loss of information. Yeah.